So today we're going to be talking about the formula for volume of a cone. Now we know the formula for the volume of a cone. The volume is 1/3 the area of the base, pi r squared, times the height. Now this formula at its root makes a sort of intuitive sense. If we were to put a cone inside a cylinder that's the same height, it would occupy some fraction of its volume. But here's the question, why is it 1/3? And why is it 1/3 for every cone compared to its cylinder? What we're going to be doing today is exploring where does this 1/3 come from without using any calculus, which is going to be a little tricky for us to pull off. This is based on a paper that was published by Professor Michael Hirschhorn of the University of New South Wales. And so we're going to be going through his work by making a few changes to his notation so it's more in line with the numbers and letters that we've been working with. I'll send a link to the paper as well, but let's go through it and talk about it as a group. So what Professor Hirschhorn did that was so clever is he didn't just look at the volume of a cone. He decided to look at the volume of a frustum. A frustum is the part of a cone that remains after you chop off the tip. So this part down here is the frustum. This particular frustum, we're going to say, has a height of f. F for frustum. The little cone that it chops off at the tip, we're going to say has a height of lowercase h. This cone has a radius of, we'll say, small r. And the frustum has a radius of its base that we're going to call big R. The radius of this base is also the radius of the big cone made up by the tiny cone sitting on top of the frustum. In addition, we're going to be talking about the area of these two bases. The small cone is going to have an area of lowercase a, and the big cone is going to have an area of uppercase A. So the frustum has on the top a circle that has a base of lowercase a, and has as its base uppercase A down there. Now it makes sense because this cone is similar to this cone, that we could say this: the height of the small cone over the radius of the small cone is equal to the height of the big cone divided by the radius of the big cone. This height divided by this radius should be the same as this height divided by this radius. They're proportional because these two cones are similar. It also makes sense to say that the area of the small cone is pi times little radius squared. And the area of the base of the big cone is pi times the big radius squared. Likewise, it makes sense to say that if I divide both sides by pi, we could get equations that look like this. And then if I take the square root of both sides, I can express radius in terms of the areas. This allows me to make a clever substitution. I can say that the height of the small cone divided by the square root of the small cone's base over the square root of pi should be proportional to the height of the big cone divided by the square root of the big cone's area over the square root of pi. Now because both of these fractions have this dividing by pi term, or square root of pi, in their denominators, we could multiply both sides by a constant to cancel that out. We're going to end up with this statement. The height of the small cone divided by the square root of its area should equal the height of the big cone divided by the square root of its area. So now let's take a look at some implications of this statement here. So if height of small cone over small area equals height of big cone over big area, we can manipulate this equation to solve for the height of the small cone. So what does that look like? First, we are going to break up this fraction, height over big area, plus height of the frustum over square root of big area. I'm going to subtract this height of the big area term from both sides. I'm going to give myself a common denominator of height of, or square root of small area times square root of big area. That way I can actually do the subtraction. This means I end up with height of big area, or height of small cone times square root of big area, minus height of small cone times square root of small area, over square root of small area, square root of, times the square root of big area, and all of that should equal the frustum over the square root of the big area. I can factor out the height of the small cone here, ending up with a term that looks like this. And I notice I have a square root of the big area being divided by both sides. So I can go ahead and multiply both sides by the square root of the big area, and that'll cancel out that term in the denominator. If I do a little bit of manipulation, I can say that the height of the frustum times the square root of the little area divided by this square root of big area minus square root of little area term equals the height. There's one other term that we're going to want to work with, and that is going to be the height of the large cone, which is little h plus the height of the frustum. Well, I can take this term for h that I have down here, f times the square root of little a over square root of big A minus square root of little a, and I can add a frustum term to it. All I've done is I've added the height of the frustum to both sides of this equation down here. If I flush this out a bit, that means we have f times the square root of a over square root of big A minus square root of little a plus f times this square root of big A minus square root of little a term over square root of big A minus square root of little a. I've multiplied the frustum by whatever this term is over whatever this term is. Anything divided by itself, except for 0, is going to be 1. So I haven't changed what this term is, just changed what it looks like. But now we have some common denominator actions going on here, and I can actually combine those terms together. Frustum times the square root of a plus frustum times square root of big area minus square root of little area, all over square root of big area minus square root of little area. H plus f is going to equal, I can factor out this frustum term, and hey, look at this. I have a square root of little area, I have a square root of little area, but minusing it. Those things can be combined. The height of the big cone could be expressed as frustum times the square root of big area over square root of big area minus square root of little area. So now I have a way of expressing what is the height of the little cone. I have a way of expressing what is the height of the big cone. So now we consider what is the volume of the frustum. Well, I know the volume of frustum is going to be volume of the big cone, the whole thing, minus the volume of the small cone, the tiny tip on the top. I don't know the formula for the volume of a cone. I mean, I do, but in the back of my head, I don't know what this 1/3 is yet. It is kind of censored out. I have a hunch that it's some kind of a constant. There is some fraction of this cylinder that is inside the cone, but I don't know what that constant is. I'm trying to solve for that one. So I'm going to say the volume of the frustum is going to be whatever this constant is times the area of the base, which is capital A, times the height of the cone. And I'm going to subtract from that the volume of the smaller cone, which should be the same constant, times its area, times its height. So the area of its base times its height times some fraction that trims off the part of the cylinder that we don't want, leaving only the cone that's inside. Well, hey, we have terms for both of these heights. Let's go ahead and do some substitution. This is going to equal some constant times an area times h plus f. That is f square root of big A all over square root of a minus square root of little a. And we're going to subtract from that the constant times the area times f check little a over square root of a minus square root of a. Makes sense so far. I'm noticing there are some things that we can factor out here. Both of these things have a constant term that we're trying to solve for. Both of these things have a height of the frustum, which I can throw there. Which means I'm left with a times the square root of big A all over square root of a minus square root of a. And we're going to subtract from that little a times square root of little a all over square root of big A minus square root of little a. I can combine some stuff. These are two fractions that have the same denominator. I can directly subtract them. This is going to be a square root big A minus little a square root little a all over square root big A minus square root little a. Which, if you are super sneaky, you might recognize as the square root of big A cubed minus the square root of little a cubed all over square root of big A minus square root of little a. Now, why is that helpful? Well, consider this. If we have a difference of cubes, x cubed minus y cubed, I can rewrite this as their cubed roots, or a difference thereof, times this expression. Don't believe me? Well, let's actually do the math. We can distribute these terms throughout to see if these two sides are equivalent. X times x squared is x cubed. X times xy is x squared y. X times y squared is xy squared. Negative y times x squared is negative x squared y. Negative y times xy is negative xy squared. Negative y times y squared minus y cubed. This x squared y and this x squared y will cancel out. This x squared xy squared and this xy squared will cancel out. And I'm left with x cubed minus y cubed. Cool. This term is the same as these two things. And if that's true, then it follows that if this equals this times this, then this divided by this should be this guy over here. Or put another way, x cubed minus y cubed over x minus y equals x squared plus xy plus y squared. Why is this useful? Well, it means if you have anything that looks like this kind of an equation, you could always rewrite it this way. Something cubed minus something cubed over that something minus something equals the little thing squared plus the two things times each other plus the other thing squared. Well, we have an equation that looks like this form. X is going to be the square root of big A. Y is going to be the square root of little a. Which means I can rewrite this equation as the constant that we don't know times the height of the frustum times the square root of big A squared plus square root of big A times square root of little a plus square root of little a squared, which can simplify to the constant that we're trying to solve for times the height of the frustum times big A plus square root of the areas multiplied by each other